Hi everyone and welcome. My name is Muhammad Al-Dali and I'm learning data science on my own. I'm going to share my experience with Code Alpha, and big thanks to Code Alpha for allowing me to participate in their internship program, where I have been assigned with the three different tasks. So let's get started. In the first task, we're going to look at the iris dataset, which is a famous dataset imported from Seaborn. So as we can see, we're first going to do some exploratory data analysis to understand the data and see some visualizations, and then we're going to run some models to classify which species of iris plant we got. So first of all, we're going to need to import packages. For sure, we're going to import pandas, matplotlib, and seaborn to be able to manipulate and visualize data. And also we're going to import some models and something related to model selection and metrics so we can work with them after we have finished our exploratory data analysis. So here we start by reading the data, which is in the CSV format, and manipulating some of the information. And here's the top 5 rows of our data. We can see we got the ID column, which is an identifier of the row that we got. Then we got some explanatory features in our data, the sepal length, sepal width, petal length, and petal width, all in centimeters. And finally we got the categorical variable species, which is going to be our target variable. Next, we're going to see some information about the data using the info method. So as we can see, there are 150 rows in our data, and all the columns show that there are 150 non-nil content, which means that there are no missing values in our dataset. Also, all data types seem to be well assigned. For example, the explanatory variables are float, and then we got the categorical variable species. Next, we can do some check before going deeper into our data. For example, we're going to check for any duplicated rows using the duplicated, chained with the sum methods, and so we can see that we got no duplicated rows in our dataset. Then we can see some description of the statistics of the main explanatory variables in our data using the describe method. So we can see, for example, that the mean for sepal length is 5.8, for sepal width is 3, and so on. And we got some information more about the standard deviation, the minimum, the 25 percentile, the median, 75 percentile, and then the max in our description of the numerical data. But what if you want to see how the data is distributed about the different species that you got? So we're going to group our data according to the species, and then we're going to calculate the mean for each explanatory variable in each species. So we got 3 different species: the Tosa, versicolor, and virginica species. And in these rows we can see the mean for each of the species in each of the explanatory variable that we got. And we want to see more visualizations, because seeing visualizations is more important to especially people that are not well informed with data science. So first of all, we're going to do a pair plot. And what a pair plot is, it's a plot that shows the relationship between different columns in our data, the numerical columns, and to see the distribution of each column on the diagonal axis. And so instead of just plotting a sheer pair plot, I added the hue argument so we can see how different things are related to the species. So that the Setosa species is colored in blue, versicolor in yellow, and then virginica in green. And on the diagonal axis, as you can see, there are some KDE plots, which are like distribution plots similar to a histogram, but like with a smooth curve. So looking at the different pair plots that we got, we can see some important feature. First of all, in many of the scatter plots that we got, we can see that, and even in the distribution plots that we got on the diagonal, we can see that the species have like some kind of ordinal information. So we can see majorly that we can start with the setosa, then versicolor, then the virginica on the axis. So it seems like the setosa at the smallest, then we got the versicolor in the medium, and then virginica. And this is pretty shown in each one of these in this information. What we can do next is to plot a heat map that shows the correlation between the different X-marathon variables. So as you can see, of course on the diagonal we got 1 because it's correlating the variable with itself. But what's more important at this 0.96 here between petal width and petal length, which is pretty sensible because maybe as the petal gets longer, it also gets wider. We can also see this information with petal length and sepal length. So as the sepals get longer, the petal length gets longer too. And also we got some other correlations, but they're not as strong as these two. We got, for example, 0.82 correlation between sepal length and petal width. However, you can see that the correlation between sepal length and sepal width is not like quite informative. We got just 0.11. So it seems that the correlation between sepal length and sepal width is not pretty constructible. So we can't judge if a long sepal is going to get us a wide sepal. So here we're going to start with the most informative visualizations. So first of all, we're going to draw box plots for each feature in our dataset, but colored by the different species. So for example, for sepal length, as we saw before in the pair plots, the setosa is the one with the lowest values for the sepal length, then versicolor comes in the middle, then virginica. And this is true for all the different features that we got, petal length and petal width, except for sepal width, where setosa seems to get the highest length, then versicolor, then virginica, then versicolor. And this shows us that in general setosa plants tend to be maybe the smaller, then we got versicolor, then we got virginica. And this is pretty useful because that's how the model is going to be trained about these features. Okay, so now that we got some pretty and useful information about our data, we're going to prepare the models to be able to predict our data. So first of all, the most common model used to classify features, our target variable, is the logistic regression model. So what a logistic regression model does is that it gathers information from a training set of our data, and then it tries to predict on unseen data. So we can see if the logistic regression model is actually training well and generalizing well to unseen data. So what we do first is to select our features that the model is going to train on and select the target variable. So the features X are our numeric data, which are the sepal length, sepal width, petal length, and petal width. Then our target variable Y is going to be the species, of course. What we do next is to split our data into a training set and a test set with the test size 0.2, which means that 20% of the data are going to be test. And we also select the random state argument in our call of the function, so that we set a seed for the randomness. So each time we run this test is going to give us the same information, so it's reproducible. So we got the train test and the test, the train set and the test set. What we do next is to initialize our logistic regression model and then fit it on our training set, X train and Y train. And next, what we need to do is to use it to predict our data on the test set. So we assign y-pred, the predictions of the y variable, the feature, the target variable, by using the model to predict on the test that we got. Then what we do is to do a classification report. And what a classification report is, a kind of seeing how the model is doing. So it shows us information about the metrics in our data, the precision, the recall, and the F1 score, in addition to the accuracy. Because the accuracy itself may not be as significant, because maybe the model have enough accuracy, but actually it has like a true positive and false positive and false negative percentage that's not quite well. So we need to see how the model does with predicting positive results and predicting negative results, and that's why you need to do the precision and recall. The F1 score is a matrix that combines between the precision and the recall, so how the model works with the predicting positive and predicting negative results. And as we can see, the model works perfectly for the Setosa species, because we got precision of 1, recall of 1, and F1 score of 1. And this means that it has predicted all the Setosa species correctly. This performance goes a bit lower on the versicolor and virginica species, so about 0.91 and 0.92 for versicolor and virginica respectively, and so overall we got an accuracy of 0.93. So we can see that the model is actually working pretty well, and we can maybe rely on it, as it's good to predict our data. What we need to do next is to build a key neighbors classifier. And what a key neighbors classifier is a similar model to the logistic regression. It trains on explorative variables and then tries to classify the categorical target variable that we got based on the distance between neighboring data and our scatter plots and so. And before running the KNN classifier, we need to tune a major hyperparameter, which is the number of neighbors that it's going to use, because maybe sometimes when the number of neighbors is low, it's going to be simple, and when the number of neighbors is too large, this doesn't mean that it's going to be working more accurately, because it may overfit our data. And what does it mean is that it's going to be to build a more complex classifier, and this may affect our data. So we need to choose the number of neighbors properly to be able to build the most efficient classifier. So here I built the classifier based on different neighbors, so from 1 to 19 neighbors, and the blue line shows us how the training accuracy is, and the yellow line shows us how the test accuracy is. And from this plot we can see that the best number of neighbors to choose is 5, because as we can see the model has its limit here, its max here on the 5. Of course we can choose key neighbors equal to 1, because it just means that it's going to copy the information. And at the same time, although it maybe works higher on the training accuracy, but we need to have a training accuracy that's relatively close to the test accuracy, because this means that the model is able to train on the information correctly, but more efficiently it's able to generalize its training to unseen data, because that's the main idea of the models, is to be able to predict unseen data. And so after tuning our model, we choose the number of neighbors to be 5, and so then the same steps are going to be reproduced again as we did with the logistic regression model. We first initialize the key neighbors classifier with n neighbors equal to 5, and then we fit the model on our training set, and then we predict on our test set, and we see the classification report that we got. So as we can see, the model, the key neighbors model, is still working pretty well on the setosa. 100% of the setosa species are correctly classified, but here we can see that the model actually works better on the other two species. So before we saw 0.91 and 0.92 for versicolor and virginica, but here we can see that the recall for versicolor is actually 100%, and the precision for virginica is 100%. And the reason we can see that these information look like mirrored on the diagonal is because when you classify some species well, but you do some wrong with other species, that means that you're going to do some wrongs on the different type of metrics on the different species. But overall we got an F1 score of 0.96, and more importantly we got now 97% accuracy, which is higher than the 93% accuracy we got from the logistic regression model. So to make things more easy to visualize, I turned the classification reports for the KNN classifier and the logistic regression model into these nice visualizations. So here on the left we can see how the model performed for the logistic regression, and here we can see how it performed for the KNN classifier, and as we can see here we got better accuracy, better F1 score, and better precision and recall for different species. So in the end we can see that we can rely better on the KNN classifier to predict our data. So I hope that I made the explanation pretty clear, and I hope we can see you in the next videos, where I'm going to share my explanation with the next two tasks that we're going to go through.